one more thing before we move on to the problem is I would like to briefly talk about radiation. So another constitutive equation, radiation. So let me write down the Stefan Boltzmann law of radiation. So this is another constitutive equation, okay, which I wrote it, I guess, yesterday. But let's clarify a couple more points here. This is the law that tells you how much amount of heat is being radiated, Q rad. The heat flux radiated is equal to epsilon sigma T to the 4. In the formula that we wrote yesterday, there was area as well, but it was not the heat flux, but the rate of heat radiated. This time it's the rate of heat radiated divided by that surface area, so that's why I don't have that A there. So you can also write it as Q over A, right? And let me get rid of this, because that's the total amount of flux. I mean, flux per unit area, but it doesn't have any particular direction associated to that. So it's perpendicular to the surface. Epsilon, as we know, it's the emissivity. And the epsilon is equal to 1 for black body radiation. Well, actually, generally for most materials, epsilon varies between 0 and 1. And the most perfect condition is when epsilon is 1. It's called black body radiation. Sigma is, on the other hand, is the Stefan Boltzmann constant. And it's equal to, in SI units, 5.676. You don't need to memorize it, times 10 to minus 8. But it's a good thing to memorize the factor 10 to minus 8. That gives you an idea about how large this number is. It's a very small number in SI units, watt per meter square times Kelvin to the power 4. And the T is the temperature of this object. Temperature of the radiating body. Okay. So if you know the temperature and if you know the emissivity, you can calculate how much heat is being radiated. You can calculate it roughly calculate it for everyday objects and how much it is, and you can actually calculate it for objects which are at extremely large temperature, like for example 1000 Kelvin, and you can have an idea about how much this changes. Since you have like T to the power 4 here, the effect of temperature is actually tremendous here. So you start to see the radiation when you actually heat up the most of the object that's around 700 or 1000 Kelvin degrees. You start to see the metals shining when you heat them, and so on. Okay, so that was all about the preliminaries. Now let's work on a problem. Let's solve a one-dimensional steady-state heat transfer problem where we combine both the heat convection and heat conduction. problem where we have both conduction and convection. Okay. So let's call this steady state conduction in a composite slab without heat generation accompanied by convective heat transfer on two sides. Okay, so our system is going to look like as follows. You have basically two materials. Let's call this material 1. Let's call this material 2. Okay. Let's call the conductivity of the first material K1, the conductivity of the second material K2, and the thickness of the first material is L1, the thickness of the second material is L2. And you have bulk fluid here. Bulk fluid 1. The temperature is TF1. And the heat transfer coefficient of this fluid is H1. And on the right-hand side, it's in contact with another fluid, bulk fluid 2. The temperature is TF2, and the heat transfer coefficient is H2. Now, this system pretty much looks like the one in the heat exchangers. So if you actually understand this system well, you can understand the modeling of the heat exchangers really well. So basically in those as well, you have a material that separates two fluids, and two fluids are flowing in either directions, and there's a material that actually conducts the heat to heat up the colder fluid and to cool down the hotter fluid. So this is a very similar system as in the heat exchanger case. Let's define our coordinates. So let's call this let's call this plus x direction. Let this be x is equal to 0. Let this be x is equal to L1, as you know, as you see, and let this be x is equal to L1 plus L2, right? Okay, so that's the description of our system. Now, what do we want to find? So we want to find out the temperature profiles. We would like to find T profiles inside the material. And we would like to find out, more importantly, the heat fluxes or maybe heat transferred from one fluid to the slabs, or from like within the slab, or from the slab to the fluid. We're going to see that like all are actually the same things. Okay. How are we going to approach the problem? First, let's apply shell balance, right? That's how we did in the previous class. As we did before. Right? And then use Fourier's law to find the T profiles. Correct? Oops. So we're going to do the same thing. And well, actually, you can say there is no need to redo this thing, right? Because I'm going to find the same thing again if I do it again, right? So what I mean is, if you do this shell balance for material 1, and you write down this is like Qx at x, this is Qx at x plus delta x. You take a shell with a thickness of delta x, this is at x, and so on. You're going to find the same thing because it's exactly the same system. It's a slab, no heat generation, no accumulation, it's steady state. So you're going to find the same equation. Again, you're going to apply the same Fourier's law. You're going to find the same thing. So the temperature in the first material will come out to be, for material 1, oops, yeah, the temperature is going to be just a linear function of position, right? It's going to be something like C1x plus C2, correct? So anybody who's actually curious about how did come from, or where did it come from? It's exactly the same linear relationship. I'm just using C1 and C2 instead of the constant, right? Okay. Just let me know if you need any clarification about this T is equal to C1x plus C2, if you think that it doesn't resemble the result we found earlier. So this is for material 1. You can label the material 1 as 1. So let's call it T1. It's basically a function of x for the material 1. Okay, so this is for x between 0 and L1, because the material 1 has a thickness of L1. Similarly, for material 2, you're going to find exactly the same thing. You can actually do a shell balance, write down the Q's, and so on and so forth. But you're going to find exactly the same formula, but only the boundary conditions are going to be different. So that's why I'm keeping the C1 and C2 there. Okay, so Tx for the material 2 is equal to, let's call it D1x plus D2. Now, I'm going to have the same equation, but I might have different constant because my boundary conditions are different. I might have different temperatures at these points as opposed to at these 2 points. So your C1 and C2 can come out to be different, but they're both going to be linear functions, right? Although they might be different functions. For L1 is less than or equal to x, that's less than or equal to L1 plus L2. Any questions so far? Okay, good. So what are we going to do now? Yes. Okay. If you use the boundary condition for the material one, for example, boundary condition for material one, the first boundary condition is basically here, the temperature. Let's call it at the temperature T1, okay? Let's assume that the temperature here is T1. Although we don't know, I just need a starting point. Here the temperature is not given as well, but let's call this one T. What do I want to call this? Okay, let's call this T0. I'm sorry. Let's call the temperature at the left T0. Let's call this T1, and let's call this T2. Okay, so the boundary conditions for the material one is going to be T0 at x is equal to 0, T1 at x is equal to L1. At x is equal to 0, t is equal to T0, and boundary condition 2 at x is equal to L1, t is equal to T1. So you actually use these two boundary conditions in combination with this equation, and then you're going to solve for C1 and C2, and you're going to find the following equation. T1 x comes out to be T1 minus T0 divided by L1 x plus T0. Okay, you can check the validity of this formula by plugging in x is equal to 0 here. You find t is equal to T0, and you can plug in also x is equal to L1, and you will find that t is going to be T1. So that makes sense. Okay, so with these boundary conditions, if you solve for C1 and C2, you find this temperature profile for the first material. And then if you use the boundary conditions for material 2, which are at x is equal to L1, t is equal to T1, at x is equal to L1 plus L2, t is equal to T2, correct? And then these two equations accompanied with this temperature profile will give you the D1 and D2. You can solve for D1 and D2. Let me do it explicitly. Okay, so from here, you see that T1 is equal to D1 times L1. So I'm doing nothing but plugging in this x is equal to L1 in this equation. Okay, plus D2, and this boundary condition gives you T2 is equal to, because you're plugging in T2 here, and you're going to plug in the x is equal to L1 plus L2 here, is going to be equal to D1 L1 plus L2 plus D2. Two equations, two unknowns. You solve for D1 and D2, and you get D1 is equal to T2 minus T1 over L2, and D2 is equal to T1 minus T2 minus T1 over L2 times L1. So you solve for D1 and D2. So you basically got the second temperature profile as well, because now you know the D1 and D2 in terms of the temperatures and lengths. So if you plug in this equation for the material 2,
can you just scroll to the right a bit? I missed something, please.
Okay.
All right, thank you.
Sure, no
yeah,
problem.
thank you.
Thank you for interrupting and asking. So yeah, it's always a good idea to ask whenever you don't see. So T2 x, if you plug in this D1 and D2 in these equations, and after rearranging, you will find that T2x is going to be T2 minus T1 x minus L1 divided by L2 plus T1. Okay, so we found the temperature profiles. Okay, now here's the question. You can say, but it's like cheating, right? We don't know. We are not given the T0 and T2, and I even don't know the T1. And is there a way to write down those T0 and T2 in terms of the given temperature? For example, the temperature of the bulk fluid 2 and the bulk fluid 1, right? The answer is yes, and that's definitely what we should do. So we should write down here. The question is, can we rewrite the temperature profiles using fluid temperatures? Also, is there a way to know T1 when T0 and T2 are given? That's another question, right? Or in other words, TF, not in other words, but or with another step included, TF1 and TF2 are given.
I have a question, Professor.
Sure, yeah, go ahead, please.
So can you go again one more time how you find D1 and D2?
Yeah, here, okay. So here's how we find the D1 and D2. So the same way as we found the C1 and C2. So look at this boundary. Oh, sorry. Let me use red. Okay. Look at this boundary condition, right? It's valid for material 2, and this also is valid for material 2, right? So what I'm going to do is basically I'm going to plug in x is equal to L1 into the equation for the temperature profile of material 2. And I should get temperature is equal to T1 for that particular x is equal to L1. So if you plug in T is equal to T1 here, right, you get this one on the left-hand side. On the right-hand side, see, you have this D1 times the x being plugged as L1, correct? Yes?
Yes.
And so you have this equation, and this D2 is basically this D2. Is that clear? That part at least?
Yes,
so,
it is.
Okay, and do you want me to clarify the rest? Like,
No, I understood already.
Okay, you understood already. Okay, great. Okay, thank you for asking. So now question is, how am I going to find those temperature? Because like here, even if I'm given these two temperatures, imagine that your temperatures are like this, and you know that it's linear, right? But it can be either like this, or maybe it's like this, right? Or maybe it's like this. You don't know what is this temperature. You know that at each material, the temperature profile is going to be linear, but you don't know how it's going to look like, because you don't have one material. You have like a composite material, so you don't know where this T1 is going to be. Is it here? Is it here? Is it here? There are infinitely many possibilities, right? So you should have one more boundary conditions to relate those. Is that clear? The question. So let's write it down. Different possibilities are as follows. For the temperature profile. Imagine your T0 and T1 is given, but you can have all sorts of, sorry, T2, all sorts of different T1 values. Is it scenario 1, 2, or 3? We don't know. So you need to have one more boundary condition. We need one more boundary condition at the interface. Okay. So here's the boundary condition, BC. It's called constant flux, or let's call it equality of fluxes at the interface. So at the interface, not only the temperature is the same, but also the fluxes is the same, because there is not going to be any accumulation in the interface. So you don't expect the heat flux coming more than coming out. So you should have exactly the same flux coming in and coming out at the interface, because you don't want any accumulation, right? So you say that at X is equal to L1, not only T is equal to T1, or T for the material 1 is equal to T for the material 2, and that's equal to T2, so T1 that is. But also, the flux Qx at L1 for the material 1 must be equal to the Qx for the material 2 at L1. So you should write down the Fourier's law minus K1 dt over dx is this Qx, right, from the Fourier's law, calculated at X is equal to L1 for the material 1, must be equal to minus K1, sorry, minus K2 for the material 2, d2 dt2 divided by dx at X is equal to L1, right? And from these equations, you find the following. So have a look at this T1, please. Right? From here, you can calculate the dt over dx for the material 1, this one. And it is equal to the derivative of this thing, which is basically this constant, right? T1 minus T0 over L1, and it's constant. It's not changing with time. So at X is equal to L1, it's also this one. So it's everywhere this value. And similarly, so basically you know this quantity, and you can actually plug it in here. And similarly, this thing is the derivative of this function. dt2 divided by dx is equal to, as you can see, it's the prefactor of the x, which is basically t2 minus t1 divided by L2. Okay, and you can actually plug this in here. And if you plug in and solve, after solving, rearranging, you will find that T1 comes out to be T0 plus K2 over K1, L1 over L2, T2 divided by, this is going to be a good algebraic exercise for you to do, plus K2 over K1, L1 over L2. Okay, so you can actually solve for T. So the T is not gonna be an arbitrary point here or here or here. It's gonna have a particular value depending on the values of K1 and K2, because depending on the K1 and K2, you're gonna have a particular flux or the temperature profile, right? And you should have the correct temperature profile, which gives you the fluxes equal to each other at the interface. Okay, any questions so far? Now what's left is, if you don't have any question, let's answer this. Now, can we relate TF1 to T0? Now, so we want to relate this TF1 to T0, right? Relate TF1 to T0. Okay. Yes, we can do it, and we can do it using the Newton's law of cooling. Right? To find Qx at x is equal to 0 for the material 1, correct? So I'm talking about this flux. That's equal to minus K1, the conductivity of the first material, dt of the material 1 over dx. And we found that this was constant already, right? We found this thing, and it's here. And but the Newton's law of cooling tells you that this flux must be equal to the heat transfer coefficient of the fluid 1, H1, times the temperature difference, TF1 minus T0. Now, how do I know which one to subtract from which? Right? Is it going to be T0 minus TF1 or TF1 minus T0? Now, let's make a comment about this. Let's be careful. It is not T0 minus TF1. And here's the reason. Since plus sign is for heat transfer towards plus x direction. So when TF1 is larger than T0, right? So if this is TF1, if this is T0, right? The heat is gonna flow from the hot fluid to the cold surface, right? So when TF1 is larger than T0, the flux will be from left to right. In other words, plus X direction, right? And thus positive. Okay. Any question about this? So it's a very common mistake that students do to take it the other way around. So but you should be careful about which way to subtract it. Okay. Now you can relate the TF1 to T0 because you can plug in this dt over dx term, and you get minus K1 T1 minus T0 over L1 is equal to H1 TF1 minus T0. So if you relate it to 2, I mean, you can solve for the T0 if you like, right? Now, but it looks still tricky, right? It looks complicated. Because now if I ask you, okay, solve for T0 with respect to TF1 and plug into the former equations and do it, oh, it's going to be a ton of work, right? But there's a trick here.